Okay, so welcome team. Today we'll be talking about the Spark internals and distributed computing, how it has evolved into a more powerful data warehousing, data analytics platform, supporting these platforms, starting from Hadoop, uh, you know, which started this distributed computing process. So basically, what distributed computing means, instead of doing a process, okay, or some task on a set of data, right? So you distribute that into parts and apply the same function or same process into all of those parts in parallel, and then you combine the sum. So that's how you can do parallel processing on the distributed data or distributed computing. Okay, so we'll talk about the DAG in with respect to Spark, Apache Spark, how it creates a DAG and how it works with the DAG. We'll talk about joint strategies, shuffling and repartitioning, or coalesce, and adaptive query execution if we get time through that. Okay. So we will be moving a little bit faster. These are all concepts, very important concepts. Whatever, whenever you go say Spark, all of these features are very important for you to talk about. In the last class, last session, we talked about Databricks Delta. So those are all the features of Databricks Delta. Whenever you talk about Databricks, you talk about Delta. What are the features of Delta? You talk about all those things that we learned, like ACID transactions, merge statements that you can use, how it stores in Parquet, time travel capabilities, vacuum, optimize, Z order, optimize, and vacuum, right? So all of those features, plus your transaction log, how it maintains a history of events on the transaction log, all of that are from the Delta. Now, when you run a Spark, when you're reading the files, right? So you're getting a data frame, right? Whenever you read a file, you get a data frame. And then, or you read from any source, or you read from your database table, also you get a data frame. Now, whenever you talk about data frame, it is distributed. So you are doing a distributed computing on your data frame. That's what you have to remember. Okay. So how is it distributed? How you should visualize distribution when you talk about any data frame, right? So let's say, okay. So let's say we have, so this is the Hadoop architecture, the old one. You don't need to worry about this anymore. It's just a representation. So there is a name node, which is also called a master. Then you have all data nodes. Okay. And then there is a local disk. So what happens is your data is distributed in all of these nodes. Nodes basically are machines. Okay. So instead of one machine, you'd have 4-5 machines. And each of those machine has some part of your data. And the name node or master will keep a log, okay, or record of which data is residing on which machine or which partition you can call. So these are all partitions of the same data. You are partitioning your data, making into parts, and then keeping it on multiple machines, so that whatever you want to work on, you will work on all of those in parallel. And when you do everything back collect, so you will have transformed data on all parts and make it whole. So that is your distributed computing. So simple example I will take. Okay. Let me 1 second. So if you just take an example here, okay, let's say I have a series of numbers as data. Okay, so I'm having 1, 2, 4, 5, 6, 7, 8, 9, 10. Okay. So this is my data on the system. Now I have a function called square. Okay. So I have a function called square, which I am running on all of the elements on the system. Okay. And then square means you multiply the element with the same element, and then you kind of come up, and then I will say sum of squares. Let's say this is the function, and this is the array or data that is set in the system somewhere. So when I run this, my squares will run on this one. Okay. And we get result. It will run on this. I will get result, right? So you will get all right. And 20, 16, 25, 36, 49, 64, 81. Okay. So let's say these are the squares. Now you have to go and sum all of these. So how do you sum? There's a 1. Okay. Then you will add, will become 1, then 5. Then you will add 9 plus 5, which is 14, so on and so forth. Okay. So let's say I will just sum this, and maybe, for simplicity's sake, I'm just doing this. It's this. Yeah. Okay. So sum is say 385. Okay. So this is the normal process. So what it is doing, it is doing sequentially on all of this. Each number, it is applying that function on each number. And then once you get it, again, it is going through all of it and doing the sum of that. So the same problem, when you move to a distributed computing, what happens is, let's say you have machine 1, or you say node 1, node 2, node 3. Okay. And then this data is distributed on the machines. So you have 1, 2, 3. Let's say I have node 1, node 2, and node 3 here. Okay. So let's say I have 1 here, 2 here, 3 here, 4. There's no logic. Okay. I'm just kind of 6, 9, 6. I have 1, 2, 3, 4, 5, 6, 7, 8, and 10. Okay. So what happens now? The square will go and run on all these 3 nodes in parallel. Okay. It's not sequential anymore. So the square will run here, this function. The square function will also run here, and the square function will also run here. And then you have a, say, a result. Then you have reduce. Then you have sum. So these are the different stages that it will have. So what is the result first is, so let's say 1 square, 1, same thing, 16 and 25. While this is computing, parallelly, this node has already computed the squares of this. Okay. And this node has also computed the squares of this. Okay. Got you? Got it? Any questions? Guys, are you able to follow?
Yes, sir.
Yes, sir.
Okay. Now in reduce, what happens? So this system has three numbers. So it has to do sum of squares. Okay. Sorry, not so square and sum of squares. Both functions, right? So we are doing both. Or maybe just sum of squares. For the sum of squares, you first have to do the square, right? So let's say it's doing that. Now, since we have done the squares, it will do the sum within the same node. Okay. So it will now count these. Okay. 25, 41, 42. So it will count the sum here, 42, and return. It will count this sum here, 40, return. It will count sum here, 164, 204, 213, 222, I believe. Something like that. Okay. So all three machines are now processed and they have the sum of squares for the part of the data they own. Okay. Now they all return and the final sum is calculated here. So this 42 will come here. Basically, let me just copy all of this. So this sum is returned to say master. Let's say I have a master here. The master gets this and the master will do the sum here. I'm doing sum from here. Or is there a difference? Somewhere we missed something. We missed some numbers. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we missed 9. Okay, let's say I have 9 here. 81. So it is 121. 121. Okay, 385. See, now the sum is tallying. But the way you processed is different. Each machine is taking a part of your task, your data, and then it is processing. The same process is run on different smaller parts of data, and then they are doing whatever function on the data they own. And finally, you add up, again, you get the same data. So the same end result is same, but how you are processing is different. This is all sequential. So it has to go in sequence, calculate the squares of each of these, and then start sum again from the top or the bottom. Whereas here, these are all independent. So while this 3 is calculating, this has calculated 3, this has calculated 3, and the fourth one. And while this is doing sum, this is also doing sum, this is also doing sum. So finally, you have one additional sum and then you get the result. So this is much faster. This is just say, let's say a small task. Now think of huge tasks that you can do, on the data that is huge, right? So let's say a million records, you have to process something, okay, on a million records. If you use one machine, how long it's going to take? And let's say if you use 20 machines, so the time is almost reduced by 20, right? So it's not exactly, but almost. That's how the distributed computing works. Okay. The same. So are you clear with the concept?
Yes.
Yes, sir.
Okay. So that's what here we are doing for the map. This is called map reduce algorithm that was done long back when Hadoop was using. But underlying, even now, it's almost like similar that we do. Just 1 second, I'm getting a call. Okay, sorry. So the same concept that we were talking about. So there are a bunch of words here, and then we want to count how many times the word is repeating. So normally you can say go one by one, dear, and then increment the count. But if you are doing a map reduce algorithm distributed, so let's say you split into three parts, okay? Each individual data will do the count of the words. And then you do shuffling. Okay, here there is a deer, here there is a deer. Okay, so you want to get a count of deer. What you do is by the key. So you shuffle the data and make sure the similar data is on one machine so that you can do the count. So deer is on this. So not deer. So okay. So deer we are moving here, and the deer here is also moving here. So all the deers are here. Car is here, bear is here, and river is here. It's not that one machine can have only one part of the data set. It can have multiple parts also. Okay. Now, once this is split, you do the count here, bear 2, car 3, deer 2, river 2, and then finally you get the final result. And don't get overwhelmed. You don't have to follow you don't have to understand it deeply. You just have to understand the concept of how the data can be distributed, processing can happen, and then you can combine. That's all. That's the concept here. Okay. um, so just think about that part. The same thing we are representing here. For example, this is a master. As I said, it has ID of 6 employees and say their expenses, worker and their expenses. And then we want to sum up all the expenses. So instead of going here, what it does is we run the sum. This is the function on 3 different workers. So worker 1 has 2 records, 4 and 5. Worker 2 has 2 records, 1 and 2. Worker 3 has 2 records, 3 and 6. So basically, it's now on 3 machines, 3 nodes or 3 partitions. Now the sum is run on this. So this total 450 is returned to master. The total here 650 is returned. Here 300 is returned. And the master is going to do the sum of this. Okay, it might look why we are complicating a simple problem. You just sum it up here. Why you have a building the complexity of splitting it, summing it, then getting back and again doing a sum, right? It looks in like that here because it is a simple problem. But if you have complex problems, okay, complex computations that you have to do on a millions of records, then this model will give you better results, best results, because the data is distributed, and whatever you say 10 rules that you want to run, 10 programs you want to run, computations you want to do, all of that can be done parallelly on different machines. And if the data is more, you can add more machines. If the data is less, you can remove the machines based on that. So that's how it works. Now when we come to Spark, how does Spark work? Okay, basically it's more or like same algorithm, master and worker. You have one node and all of that. So basically you have a driver program and a Spark context. There is a cluster manager. These are worker nodes. What does the cluster manager do? It manages the communication between a master, Spark context, and the worker nodes executors. The driver program has the Spark context, which will assign the jobs to the worker nodes. The worker nodes have these small boxes, you see, task. So first it will have an executor, and within the executor, you will have tasks. So each executor can execute one task or number of, say, basically, the cores, machine cores, 2 cores, quad core, 8 core, 16 core. Have you heard of it?
Multiprocessor?
Yeah, in all your machines, laptops, you will have cores. When you say properties, it will tell you, is it a 4-core machine or 16-core machine or 8-core machine? Quad core means 4 cores. So basically 4 blocks will be there, computation blocks, which are parallel, independent. So if it is a 4-core machine, you can run 4 tasks in parallel on that machine independently. So that is your hardware, the chips, the board that you have, the number of cores. If you go to your machine, you go properties, where it will shows the OS and whether it is, what kind of RAM it has, AMD or Intel chip, all of that, right? And RAM and hard disk and all of that. There it will also tell you how many cores it has. So basically, based on number of cores is your parallelism, like how many tasks you can run in parallel. Okay, if it is a 16 core, you can run 16 tasks in parallel. So that is executor. Just like the other day we were talking in parallelism about the Kafka cluster, right? So number of what you call the consumers in the group and the partitions they can read, right? So the maximum parallelism is based on the number of partitions that you can read in parallel. So you can go up to the maximum number of partitions you can create the consumers. Similarly, when I say I can run the task on the partitions in parallel, these are all the tasks. So each executor can run the tasks again based on number of cores it has. It has 4 cores, and if you give 10 tasks, it will do the first 4 tasks, then it will take the next 4, then it will take the next 2, like that. But you can add more machines, more worker nodes if you want more parallelism. But so this is how it will work. Okay. This is just to have a understanding of how the parallelism or the distributed computing works on this. Okay, parallel computing. This is the DAG. We will come to it. Basically, you can look at it. This is where we will come to after we run our jobs. Okay. So what this is showing is what are the different stages. So you see here stage, right? There is a whole stage code gen. There is something called exchange, and then shuffle query stage, whole stage code gen, whole state code gen, exchange. There is a sort, then there is exchange, merge here, and then there is exchange. There is whole state code gen. 1, 2, 3, 4, 5 stages. How the Spark is doing the executing the job. DAG means generally DAG is called directional acyclic graph. It's basically, if you see here, it has a direction. It moves from left to right. Okay. Acyclic is it does not move back direction. It's only in one way. Okay. It just moves forward. It does not go back anywhere into the stage. So once the DAG is created, it follows that path to complete the job. So we will come here. I will show you. So we will go back and see how this is built in our program. Okay. In the Spark. So we will talk about, so what do we want first? Okay. So we'll talk about caching, we'll talk about joint strategies, and we will talk about DAG. Okay, so let's first go about DAG. So before going DAG, so you know how Spark evaluation program, what is called lazy evaluation. We have talked about it, lazy evaluation. So what are the two different types of functions in Spark? You may not call it functions, but Spark has two types of execution functions. One is transformations and the other is actions, right? Remember? Transformations and actions. So whatever you do, all of this, these are considered as transformations.
Satyam,
And
मैं बेटा
yeah, Anshul.
sorry Arun.
Oh, no, I thought you were talking. So transformations, and this is the action. Action is you want to do something now. Okay, what it is, whether it is display or write. Okay, so these are all the actions. So you can check what are the Spark transformations and actions. Okay. What are the Spark and RDD? Let's see if we have. Does it show? No, this is all applying functions, selecting data, mathematical functions, Spark control. No, that's fine. Okay. So these are all the transformations: map, filter, flat map, reduce by key, group by key. You have used group by, right, already. So you are doing group by in the data frame, correct? Then union, intersection, repartition. So these are all transformations. Actions are this: collect, count, reduce, take, for each, save as, show. So these are all actions. Or write. Write is also an action. Something same as like save. Write, then you say save as, right? So these are all actions. So when you do a transformation, there is no job created or there is no computing that is happening. It just creates a process map in memory or a DAG it creates and keeps it for reference. Only when you do an action, then it will figure out, hey, there is an action. Now I have to do something. To do that action, what do I need to calculate? So it will go back in the DAG and whatever is needed, it will go and calculate those transformations required for the action. So that is called lazy evaluation. If you write 100 lines of code and you don't have an action in that, it doesn't do anything. It just goes through the 100 lines, creates a map, and just keep it. So there is no computation that is happening. Got it? So these are like in Spark, transformations create new RDD, or you can say data frames. RDDs are now old without triggering execution, while actions perform computations and return results, okay, which will triggering of the Spark job. So that's what you have to remember. Transformations versus actions. Okay. So now the same thing here. Oh, I have not created a computer. I have to create it. Okay. While the compute is happening, what we will do here. So what we are doing, we are creating a data frame with just some elements, spark dot range. It's just like an array of numbers, as I was showing you on the spreadsheet, 1 to 1000. Now I am doing a expression as id star 5 as id, so 5 times. Okay, and then I will display it. So each number, simple numbers, it's going to multiply with 5. This is the expression that you use. So it will go through the data frame, each element, and then multiply by 5. So this multiplication is again a transformation. There is no action. Okay. So if I don't do anything here, if I don't display and run this, uh, okay. So if I run this, it will just waiting for. Okay. So see, there is no Spark job here. It just has written a the what you call the structure. Okay, the structure of the data frame, what it would be look like. But there is no Spark job that is triggered, which means there is no computation that has happened yet. So please remember this. I'll tell you in any of the interviews, please talk about these concepts, Databricks Delta concepts or Spark internals, right? They're pretty impressed. Talk about any question that comes with Spark, just throw in 2 lines. Say, hey, Spark does lazy evaluation, like it has transformations and actions, and then it creates a DAG. Well, computation happens only when you have an action, but transformation does not trigger any computation. It just gives you a structure, and return a data frame kind of a thing. So if you just throw in these kind of concepts, it gives you a very good impression. Okay. So these are like very basics function. Now, when you do this, then you get a DAG. When you run this, there is a Spark job, and the Spark job will trigger a job. Now, when you go to the job, you go view. So this is your Spark job, and I'll open it in a page here. Okay. So this is the monitor where it will show you all the details about your job. Status submitted, duration, SQL query, job group, completed stages, event timeline. These are all your executors, Spark executors. There is one executor driver added because you only have one executor. Because it's a what you call community edition, and your compute has just one machine. If you have multiple machines, you can see all of that here in the executors and stages. They will ask you what are all there in the Spark UI, what you can see. Remember this, in the Spark UI, you can see DAG of how it is executed, stages, jobs. There are the tabs, right? Jobs, stages. You have to remember this, all of these tabs, or at least 4 or 5 these. Jobs, stages, storage, environment, okay, executors. It will show all the executors here. You don't have to talk about each individual, right? But thing is, you have to remember what are all is available on this Spark UI. SQL data frame. If there is a C here, this is a data frame. You will have this. Then it talks about how this data frame was created, simple numbers, time 5, and all of this. JDBC, if you have any connections, streaming, structured streaming, you have any streaming query, it will show here. So these tabs, you should talk about jobs, stages, environment, SQL, executors, and all of that. Now, if you come here in the jobs, there it go. The DAG go. Okay, let me come back here again. Yeah, here, DAG visualization, right? So here it will show you shows a graph of stages executed for this job. Okay, each of which can contain multiple RDD operations. Example, map, filter, and of RDDs inside each operation shown as dots. Okay, so RDDs inside each operation are shown as these dots here. Remember, there is only one stage here in the job, and it is in sequence here that is happening on this stage. Any questions? Pay some attention. These are very basic concepts and important for your from the interview perspective. Okay. Now, so this is display that has happened function. Now I'm going to create another data frame with the range 1 to say 1 million or 10 million, whatever it is, 1 million, and skipping the alternate numbers. Now here I'm doing more numbers dot repartition 7. So I think before going here, what I will do is, so any data frame, okay, basically any data frame is always distributed, which means it has partitions, multiple partitions, and it is distributed across your nodes. One data frame. You have to always visualize that a data frame is always distributed. It's not there on one machine. It can be, but it is always in parts, broken or cut down in parts, and on different nodes of the machine, had different partitions that you have to visualize. Anything you do on a data frame is always distributed computing. Okay. So how many partitions do I have? How do I know? So I say display more numbers dot RDD dot say get num partitions. Let's run this and see. See here, how many partitions it has? Guys, are you there?
You already said, right?
Yeah. So this data frame is split into 8 partitions. So the parallelism is 8. Whatever operation you do, it runs on 8 partitions. Okay. Sometimes the partitions may be empty as well. There may not be any data. The data frame is divided into partitions, but some partitions may be empty. That is a different thing that we'll talk about. But say there is 8 partitions here. Now, what I'm doing here is I am combining those partitions, or basically repartitioning them. I'm moving around the data. So let's say you have some flour, you have put in 8 cups. Okay. Now you want to just make it 7 parts. So you combine everything, or you just took some from one cup and then distribute in all the remaining seven. Somehow you just redistribute and make it 7 parts, 7 cups. Okay. So same thing here, repartitioning will redistribute your data into these 7 partitions. Now, if I do this, okay, and we do here, C split 7 and display partitions and run this. See now how many partitions I have?
7.
7. So you can repartition your data. So why you want to repartition your data? I will tell you. Basically, let's say default, when you read some file, it will default create 200 partitions. And then your data is distributed into 200 partitions. Sometimes you may not have enough data in all 200 partitions. You may have 100 partition data in 100 partitions or 150 partitions, and the rest 50 are blank. But when you execute any function, it's gonna run on all the partitions. So it will go and check in the partition, but there is no data, so it won't do anything. But still there is an overhead of going and checking that partition, trying to run that function on that partition and see there is no data and come back. So to avoid those overhead, we will repartition it. Okay, so that now it will make sure all partitions have data. Or sometimes it's called what is it called? Skew. This is also very important topic or question that's asked. What are the issues, performance issues with Spark? You have to always talk about data skew. You can read more about what is data skew and how you can solve it using salting technique. It's called salting technique. But data skew happens just like this, say 8 partitions and you have 1,000,000 records. Just say first partition has, if you have say 10 partitions, how many numbers each partition should have? If you have 100,000 and 10 partitions, each partition should have 10,000, equal distribution. But say for just for assume that all 9 partitions have only 1,000 records. How much data will be in the 10th partition out of 100,000? 9 partitions have 1,000. How many records will be in the 10th partition? Guys, you don't know math or you don't want to talk?
It's 99, right? 99.
Yeah.
Okay.
So 9 partitions have 1,000. So 9,000. So the 10th partition will have 91,000 records.
91.
Numbers.
Okay.
Let's say if I'm running the same function of square, all 9 partition will run in the same time because they have only say 1,000 records. So they can do fast and they complete it and they wait. The 10th partition has 91,000 records to do the processing. So it keeps on going, it keeps computing because it's a lot of work to do, right? But the entire job is not completed until all the tasks are completed, all the partitions are calculated, right? So the ones who have finished early, they have to wait for the last one to finish. So the time taken is the elapsed time by the last partition, which is heavy. Now, so the first 9 say took 1 minute each, 9 minutes, and the last one would take 90 minutes. So what is the total job? How much time the total job has taken to complete?
180 minutes.
190 minutes. How 190 minutes? So first job has taken 1 minute, right? For calculating 1000 records. Second also has 1000 records. It will take 1 minute. Third has same thing. Fourth has same thing. 5, 6, 7, 8, 9. Now the 10th record has 91,000. So how many minutes it will take? Roughly 91 minutes. Right? Now the total time of the job is, if it starts at 9 a.m. for example, the partition 1, the task 1 will finish at 9:01. When will partition 2 finish?
Same time.
Same time, right? Exactly. So all of this will finish at 9:01 because these are all parallel. These are happening, computation is happening in parallel. Okay, distributed computing in parallel. Now this will finish at 9:01. All of these will finish at 9:01. Okay, but this one cannot finish at 9:01. It takes 91 minutes. So it will complete at the 10:31. So when will the job complete?
10:31.
10:31.
So the job will complete at 10:31. So the time taken to do this calculation is 10:30. This is 91 minutes, not 1 minute. This is happening because of data skew. One partition has very huge data than other partitions. Basically, the partitions are not evenly balanced, the load or data on these partitions. To kind of solve this, you can do a repartition. Sometimes it will help. Sometimes it will not help. So you can do sorting technique. Basically, you have to add some value to the key and redistribute repartition based on the key. Now, let's say for simplicity, I am doing repartitioning. Okay, this data shuffling around and then get back all of them to say 10,000 records. And then each will take at 9:10, right? So each will take 10 minutes, 10,000 records. So the 10th will also have 10,000. So it will take 10 minutes. Now the job will finish at what time? If each of the tasks takes 10 minutes, all 10.
10:41.
10:41. I'm saying it started at 9. So after, say, let's say, okay, this is the one. So now after redistribution, I did a repartition. Let's say basically redistribution of everything to again 10, or let's say I did 10, but now the data is evenly distributed. So everything has 10,000 records. So everything will take 10 minutes. So this will finish at 9:10.
19.
So everything will finish at 9:10. Okay. Now tell me, when does the job finish? If each partition finishes at 9:10.
Job will also finish at 9.
So job will also finish at 9:10. Now the total processing time for the job is
10 minutes.
10 minutes. Yeah.
Right. So that is the distributed processing, parallel processing. So now the partitions has to be evenly balanced. So if some of the partitions are out of sync or not balanced, one of the tasks might be running longer because it might be working on that partition which has a huge data. That's how you have to go and check the UI and see which task is running longer, what is the issue with that. Is it a network problem on that? Is that network slow? Or is it a machine that is not responding? Or is it the huge data that it is processing on that node? So these are all the things that you do to troubleshoot a Spark job that is running for a longer period. Okay. Now here the job will finish in 10 minutes. That's how it works. You can read about the salting technique. Okay, what salting technique means and what data skew means. You can go and refer and talk about that. Now coming back, so it's still not done. So I am doing a take. Take is also an action. Take means it will collect, it will go read the data and take 2 records out of it and then display. So now I'm running a like say now it is row ID this and row ID this. It is taking out 2 IDs. As soon as I do this, there are Spark jobs that are executed. So I go here. Sometimes if there are additional 2 jobs, you don't need to check that because it will skip the previously jobs. It just triggers those jobs, but it will trigger. But see here, we have this job, first job here, and then exchange. Why is this exchange? What is exchange? What is it exchanging?
Partition, due to partition change.
So when you're doing repartition, so it is data exchanged between the partitions. That is the boundary when there is a new stage created. So whenever there is a new stage created, there is a data shuffling, data exchange that is happening. It's called shuffling. Okay. Remember that Spark creates a DAG and it has multiple stages. A new stage is created whenever there is a data shuffling happening. Data is moving around. When does data move around? When you do repartition or when you do a join. Okay. So when you do a join, coalesce, and repartition, these are the operations where we'll create a new stage. So here we are doing repartition. So there is an exchange. Then there is a new stage that is created. Clear? Can we move forward? Any questions? Ramya? Anshu?
No, no hurry.
Good, clear? This is very, very important topic. That's why I have put it late in the course, because first you need to be comfortable with all of these Spark, data frame, batch processor and all of that, so that it will be, you can relate to what is happening when you do the computing, right? So now I'm creating bunch of data frames here. 1, 2, 3, 4, 5 data frames. First one is this, 1 million records. Second one is also this, 1 million records with say this, skipping one number each. So alternate numbers it will take. Data frame 3 is built on data frame 1. When I repartition to 7, data frame 4 is repartitioning to data frame, repartitioning the second data frame to 9 partitions. And data frame 5 is I am doing a expression on data frame 3. And then I'm joining the data frame 5 with data frame 4 on ID. Then I'm doing a sum on this data frame. And then I'm calling show. So all of these operations are happening on this. Okay. So 1, 2 data frames. There is a repartition. There is another repartition on this, Then there is a map or there's some operation happening on this data frame. Then I'm joining 2 data frames. Then again, some operation happening on that. And then we are doing sum. So let me run this and then see how the DAG comes out and then how it is related to this. So now while this is running, tell me, is this a transformation or action?
What is happening is action.
So this one. What is the action in
one
all
is
of
transformation.
this?
Yeah.
What is an action in all of this?
Sum dot display.
Sum dot show, last one.
Yeah. Sum dot show is the action. Okay. Now I have Spark jobs, I have all of these happen. The sum is displayed here. I'll go and I'll just click on the last job because all of these will be also available here. Basically, if you do this, it will show the first job as the DAG here, stage 6. If you see here, stage 6. Then if you go to the next job, stage 7, okay. If you go to next one, see stage 8. So it has skipped this and then created a new stage. Okay, 9. So same thing. So we go to the last one because we know we are actually doing all of this here and see this is the DAG we were talking about. The first one you can see is the first data frame. Second data frame is this one. Let's close this. So first data frame DF1, DF2, and these are two repartitions. So that's why there is an exchange. Okay, so you can see here connection RDD3. So this exchange comes here and there is a repartition for this data frame. This exchange creates this. Okay. Now this whole stage 17 is because I'm joining DF3 and DF4. Sorry, not DF3, it's a DF5 and DF4. This is the joining. So this is select expression. I said, right, whatever data frame you're working on, the map or any transformations will be in the same stage. There is no stage created for that. Okay, so there is just a whole stage code gen. So this is where your calculation is happening on this data frame. So then it will, this is the join between two data frames. What are the data frames that you're joining? DF5 and DF4. So DF4 is basically the DF2 repartition and DF5 is built on DF3. So this is built on these two. Here, this is the repartition and the some processing happening that comes here and this exchange is here. So these two are joined here. There is a sort before joining. By default, it will have some sorting before it joins the data sets on ID. It's like a SQL, right? You know SQL joins. So it's joined both the data frames. And then there is a final exchange here because you run the select expression and sum.show. So all of that is the final whole stage code gen. So this is how your DAG is created. At each stage, wherever there is a data transfer, the repartition, it will automatically create a new stage. This is how all of these stages are created when you run this script on this program. Clear? So this is about the DAG that you have to remember. Now, if you go here, it will have all the stages that were run. Skipped stages is fine because once it is calculated, it will not run. So what are the tasks? There are 8 tasks. Okay, because 8 partitions, it will run 8 tasks initially. Some of the tasks it might skip. You can do the executors. So you see here, there's only one executor because we have a single node machine. So there will be only one executor, which is your driver. There are no workers. So everything is done on the driver here. So then you can go SQL data frame. It will show DF1, more numbers, ID, simple numbers, all of these which were executed, the Spark SQLs on this compute, basically. Okay, so that is the DAG part. You understood? Clear?
Yes, sir.
Okay. So next thing, let's go and look at caching. So what does caching mean? Anyone? Narsimha, what does caching mean?
Like, is it like the cache memory which we have?
Yeah, cache memory. Yes, Ramya, how does caching help? You're on mute. You there? Okay. So how does caching help, Anshu?
So caching helps in computing faster. So the queries which are some of the queries which are repeatedly used. So if we keep that kind of data in the cache, it will give you the pre-processed result.
Right, exactly. So when you are looking for some data which is already calculated or retrieved earlier and you cached it, next time you want to get the same data, you don't have to again calculate or process or go and retrieve, get it back. You can just take it from the cache, which is already pre-calculated and kept in the memory. So that is the caching. Remember last time when we talked about Snowflake, we said Snowflake provides a what you call warehouse cache and query cache. So any query you execute, the results will be in cache for 24 hours. So within 24 hours, anybody who execute the same query, it will not go and calculate or get data from database, but it will return from the cache. And if there is any changes to the query, it will go and fetch the new results and again cache it for the next 24 hours. Basically, so that's the caching. Now here we are seeing, right? So whatever we do, we have the data frame. So whenever you run the data frame, it will go back and it goes through the DAG. What is the dependency? And all the dependencies it will start and start calculating all the data frames or all the dependencies. Now let's see how all of this works. So I have a files, Amazon data files in this folder. Now I'm going to create a data frame with some operations on these files, whatever it has read the CSV file. So forget about what is cast, what is alias. I'm just trying to see what computation happens and how we should use the caching. Okay, so these are all like Spark processing and how you improve the performance. Okay, troubleshooting and performance. What we talked about earlier, distributed computing improves the performance. You can have multiple nodes. You can repartition to make sure the troubleshooting. If the job is not performing well, some of the tasks, if it's a data skew, you can do repartition or salting and make it faster and fix the issue, right? Troubleshoot that using the UI, Spark UI. So here, how caching can help improve the performance. So this is data frame 1. So there's still no action. All of this is just reading and creating the data frame. So data frame 2 is built on data frame 1. I'm filtering data frame 1 where discount price is greater than 10,000. So remember that this is just another filter. So I'm creating a new data frame by filtering some data from the data frame 1. Again, there is no action. So there is no Spark job. It just make a mental note of, okay, DF2 is dependent on DF1. I have to do some operations on DF1 and get a new data frame called DF2. Now I'm doing DF3. which is on the DF2. Okay. On DF2, what I'm doing, adding a category column where I'm adding main category and subcategory. I'm just concatenating those two columns and creating a new column in the data frame 3. Again, there is no computation because there is no action yet. All of these are transformations. DF4, I'm depending on DF2. Again, another column with column, more discount. I'm just taking a new column, taking a discount price from DF2 and subtracting 5,000 from it. So there is another data frame, DF4. Again, no action, just transformation. So it just compute. DF5, another data frame, which is again dependent on DF2. Name image, I'm adding DF2 column name and column link, concatenating these two, adding a new column and calling it data frame 5. Okay. Pay attention. I have created 5 different data frames from one data set and how each data frame is dependent on the others. So I'm doing what I'm doing here now. I'm going to call an action. Okay. It's a count or display, both are actions on data frame 3. Right? Now, if I say data frame 3, what is data frame 3 dependent on? Let's go back and see. Data frame 3. Data frame 3 is dependent on
Data frame 2.
data frame 2. Now, where do I get data frame 2? Data frame 2 is calculated from data frame
Data frame
1.
1.
So where is my data frame 1? Data frame 1 is calculated on DF. Where is DF? DF is my data set that I read. So basically, if I have to get DF3, I have to get data frame 2. Because DF2 is dependent on DF1, I have to get DF1. And because DF1 is dependent on DF, I have to get this data set read. So this is the dependency here. Okay. DF3 dependent on DF2, dependent on DF1, dependent on DF, which is a Spark read. Now, if I run this, now it will run the Spark jobs. So check the time here. Keep a note of time. How much time it has taken?
15 seconds.
15 seconds. Okay. So to calculate this, it has taken 15 seconds. Now I am calculating DF4. DF4 is dependent on DF2. DF2 is dependent on DF1. So we can go back here and check. DF4 is also dependent on DF2. DF2 is dependent on DF1. Same story. DF1 is dependent on DF and Spark read. Right? So this is the dependency or DAG. Now, this is run. So I will run DF4. How much time it has taken?
12 seconds.
12 seconds. Now I'm doing DF5. So DF5, same story, dependent on DF2, DF1, DF. Okay, because say DF5 is dependent on DF2. So DF5.count, if I run, it will run and give me steps. This. Okay, so how much time it has taken? 14 seconds. Oh no, sorry, 11 seconds. Okay, it's 15, 12, and 11 seconds. Okay. If you look at the Spark jobs, we go here. So there is stage 24 and stage 25. I think because it has already done the stages. Let's go to DF4. Again, this whole stage code gen, stage 28. Oops, sorry. Seconds. So same thing here. Stage 34. It has done all the data frames, calculated, and then provided the whole stage code gen. Now, what is common? What is the pattern here? You see, what is the common pattern?
Dependency.
Yeah. So dependency. What is common in the dependency? All the data frames are dependent on DF2. Of course, DF2 is dependent on DF1, DF, all of this. Okay. But all these three different data frames, they are all dependent on DF2. So what I will do is I will go and cache the data frame 2. I will calculate the data frame 2, and then I'm going to cache that, which is if I cache this data frame 2 here, now this df1.filter, reading from the files, and then select, all of these will be cached. Okay. So I will go df2.cache. So I will run this. So df2 will run the df1, read, and everything, right? So I'm just right now going here and calculating the df2, which is fair enough, taken 14 seconds, and I've done this. So see here, there is a new thing that has come up, in-memory table scan, and there is a green dot. So wherever there is a green dot in the DAG, it means it is the cache. So it is accessing the cache, or it is it is hitting the cache, saving it in the cache. So this green dot. Okay. Now I have cached it. So there is a green dot here. It's taken 14 seconds. Now I'm going to do df4.count, which is same as this df4.count. Same operation I'm going to do again here. Now see how much time it has taken. How much time it has taken? df4?
1 second.
1 second. Here, 12 seconds. Right? The same operation, just because we have cached the dependency. Okay. Why it has taken 1 second? If you go here and look at this, you will see the same green dot, that it is accessing the in-memory table scan cache instead of going and reading all the stuff again from the files, reading and all of that. Once you read it, you have cached it, so that all further data frames which are dependent on that will use that cached data frame in the cache. Now, if I go df5, says less than 1 second. Same thing. If you go here and check, you will see the same green dot. Okay. Now, df3, same thing, less than 1 second, same green dot you will see here. Green dot. Now, what I will do, I will go and remove the cached df2 data frame. Okay, you might be saying, hey, we don't know whether actually the cache is doing it or it's just doing it because you are running it multiple times. So I will just remove the df2 from the cache. Now I'll go back and run the same things again. df4.count, which took 1 second earlier. See, now it again takes whatever 12, 13, 14 seconds. 10 seconds. Okay. So you can try any of this. All of them will take the same time because it's going to go back and reprocess, recompute the data frame 2 again and again every time you go and access df2 because you don't have a cache right now. Okay. So what are the caching options? You can do cache df data frame 2.cache. Okay. And then there is something called persist. Persist means it's the same as a cache, but will give you different options on how you want to cache it. Cache is equal to memory. Okay. Which means by default, if you use cache, it will try to cache the data frame in the memory. Now, for example, let's say you have read a 10 GB file and you have only 4 GB RAM and you use cache. What happens? It will try to fit all 10 GB into the 4 GB RAM and it cannot fit it. So it will gonna spill out. It says you get out of memory error. So to help with that, what you can do is it will give you different options. If you use persist, you can still go and use the same memory to cache. You can do memory and disk, which means out of 10 GB, let's say you have 5 GB memory. So it will store 5 GB into the memory and the remaining 5 GB to the hard disk. Hard disk you will have like 100 GB or 200 GB, whatever hard disk you will have. So it will write to the disk of the machine. Disk only means, okay, it will not store in the memory, but it will write to the disk. It will get from the disk. Memory serialized and disk serialized means it will write to memory, but before writing, it will serialize the data. Serialize, unserialize is something, concept to compress the data and write it. But there is an overhead of uncompressing when you read, but the overall benefit is more. When you see the overall benefit is more than doing a serialize and deserialize, then you can use it. Disk serialize, same thing, but it will write serialize and write to disk and then get from disk and deserialize. Memory and disk serialize is same as here, memory and disk, but 5 GB it will take, serialize, write to memory, 5 GB it will take, serialize to disk and write to disk, something like that it will distribute. So these are two options. By default, if you use cache, it is same as using persist with memory. So everything will be in memory. So that is how you do the caching. Got it? So this is how
Yes,
Spark does the distributed computing using Spark context driver and worker nodes. And it kind of distributes the data into partitions and runs all the operations on the partitions. How you can do partitioning, repartitioning, how it creates a DAG to execute. And it executes only when there is an action, not when there is a transformation. And the DAG has stages. Whenever there is a data shuffle or exchange, there is a new stage that is created. Data shuffle happens when you do what? Repartition or joins of the tables. Then there is a data shuffling happens. Data shuffling is costly, so you should avoid as much as possible data shuffling. Then there is a new stage created, but basically you're trying to redistribute data between the nodes. There is a data transfer that is happening over network, okay, between the machines. So it's always going to cost you IO and memory and network and all of that overheads. So it is to improve the performance, you have to make sure you try to minimize the data shuffles. You try to make sure all your partitions are balanced. You try to make sure either coalesce or repartition. Coalesce is also repartitioning, but it will only reduce the number of partitions. You cannot increase the number of partitions using coalesce. But repartition, even if you have say 8 partitions, if you want 100 partitions, you can do repartition 100. So it can increase or decrease partitions, but coalesce is only to reduce the partitions. So those are the performance optimization that you have to do. Is you can reduce the data shuffling as much as possible. Make sure the data is evenly distributed. You can use repartition or coalesce for that. Make sure your all the partitions have data, and make sure you can do the caching to reduce the performance. Or troubleshooting, if a long time it's taking a long time, you can go and check the UI and solve the data skew either by repartition or sorting technique, by adding a key, by adding some random values to the key and doing a reshuffling of the data, repartition of that by that key, right? So these are all the troubleshooting and optimizations that you can do for Spark, and also how the distributed computing works, how data frame is distributed in the Spark, and how the Spark parallel processing or computing happens with the master and worker nodes and the cluster manager and the driver context driver. Cool. That's the summary. Any questions? I had one more topic, but I think we are out of time. We cannot run. So I'm not sure. So we may not have classes on the weekends. This Saturday we'll not have. Sunday I will check. But whatever remaining classes that we have, we'll be doing weekdays, same time, Monday and Thursday most likely. There will be another 3 or 4 sessions. So another week or 2, as I said, before the end of this month, we will wrap up, and be prepared for the certifications. I will send you some data dumps that will help you, but you can go ahead and maybe start register for the certification exam for Databricks. Any questions? Nasima?
Yeah, no
Anshu?
question.
No, Arun.
Nabi?
No, Arun, I'm good. Yeah.
Ramya?
No hurry.
Raju?
No from mine.
Okay, all good. Everybody understood, or it's a bouncer or something like that. Understood the
Yeah, no,
Yeah, no,
concepts?
this is very nice. Yeah, this is very nice. The performance is concepts are very important for the interview perspective.
Yeah, definitely. Any interview, they will ask
Mm.
definitely how do you improve performance? How do you troubleshoot, right? Issues. They're just looking for these terms, whatever we have discussed today. That's why I said it's very important. And there's one more is specific to Spark. What it does is the join strategies. When you join 2 tables, because there is a lot of data shuffling that happens. Remember, I told you data shuffling is bad for the performance. Think about hundreds of GBs of data that you have in tables, and then you're trying to join, and then the data is shuffling all over the network. So it's very, very bad. So to solve that, Spark has adaptive query execution, an engine that can optimize your joins, but it has 3 join strategies that it employs to go through that. To deploy, to reduce the shuffling and to make the joins faster. Okay, we'll talk about it, or you can also look at it. It has broadcast hash join, shuffle merge join, and shuffle sort join. So the 3 types of join strategies it uses when you join the tables. See, join types of joins is different, join strategies is different. When you say when they ask you types of joins Spark supports, you should ask them, are you talking about the SQL joins like left join, right join, inner join, self join or cross join. These are the SQL joins that are supported. Like Spark also supports all of them. But if you talk about join strategies, there are 3 distinct strategies that Spark employs that we'll talk about. But for now, I think you have let me see if I have. I don't have it right now, but yeah, I will get that to you in the next class. What are the join strategies and how we deploy them? It's just a concept, but if you have time, do read it. Spark join strategies. You will see those 3 strategies basically. Spark join strategies. Just give me a couple more minutes. We'll wrap up. I have that somewhere, but I'm not able to find that now. Yeah. Okay. Got you. So let me share this. So this is the join strategies. One is broadcast hash join and shuffle hash join. And then there is a shuffle sort merge join. These are the 3 strategies. I will show you how this work in our next session and in the code also notebook, how this will impact or you cannot see maybe the performance, but we can see the query execution, what kind of strategy that it is using to join the tables. Even if you don't understand exactly all of this, at least you should know 3 strategies and definition of how that is. At least at that level, it's good if you know. Should be good if you know. Okay. All right, guys. That's it. Thank you so much. I think we are over time. If you have any questions, reach out to me. So we have published the. I have published the assignment or project, first project. So I will add a couple more or make changes to this one. But just go through it, start analyzing. I will add more details later. Okay.
Okay, Karan.
All right, guys. Thank you so much. Have a good night. We'll meet again.
Thank you, Arun.
Good night.
Thank you.
Sweet. Thank you.
Thank
Bye.
you.